Okay, and there's already a whole bunch comes up. Okay, evaluate solution of a differential equation problem. Solve non-stiff. The OD45 is what basically kind of what you should always try first when you do solutions to differential equations with MATLAB. Okay, so let's just look at the documentation for that. And again, this is very sophisticated. There are a gazillion options here, which you don't have time to go into. And we're going to use the most simplest form. Okay, look at that first line over there. See where it says ty equals solver, sorry for the small print, of OD function t span y0. Now, it doesn't say OD45 there, because what happens is that there are a whole bunch of solvers that MATLAB has. There's an OD45, there's an OD23. So this is kind of, can be anything. In our case, it's OD45, okay? But since they try to keep the syntax the same, you know, they just say whatever solver you want to use. Okay, in our case, we use OD45, okay? So let's see what goes in there. What's the inputs, okay? Obviously, you need something that calculates the derivative, right? I have to have some routine. I guess the t and the x will come in, and it computes the x dt, right? Obviously, that's got to be in there someplace. And of course, it's our job to write a routine that will do that, a function which will do that. So that's basically all the work we really have to do. Okay? Give me a t and x, compute dx dt. Okay. What else is in here? There's a thing here called t-span. T-span actually is a two-element vector. The first element is where you want to start, which is in our case is -2. That's always where the initial condition is. And then where do you want to stop? Let me see now. I'm going to go to 15. So integrate. Remember, when you do this thing, you're not getting an analytical solution, so you have to tell MATLAB, okay, I know the value at -2, where do you want me to march to? You want to go from -2 to 8? -2 to 15? So let's integrate from t equals -2, where the initial condition is, to the point, I think I did t equals 15. Okay, let's choose something. And that's basically what this t-span is. It's a two-element vector. It's a very good name. You know, again, you can call it anything that you want, but basically it kind of spans where the solution starts. So t-span is a two-element vector. We'll put the first element equal to -2. Be very careful, not 0, because MATLAB will assume, okay, that the first element of t-span is where you're starting, where your initial condition is. You have to be very, very careful about that. So the first element of t-span, as we'll see, will be -2. The second element is where we want to stop, in our case 15. And then you've got y0, in our case, the initial value of the dependent variable, okay, which in our case is going to be 0.55. Okay, so we've got all the input arguments. Now what happens when you come out? Just think about it, okay? I want to get a graph basically of y versus t, okay? It's all numerical, right? So what's going to happen? You have to give me a vector t of values, t1, t2, t3, t4, and the corresponding y's, so we can use the plot function to see a picture of it, right? So what comes out over here is that the output of this thing, t and y, they'll be vectors of the same length, okay? And t1 will go to y1, t2 go to y2, so you can just do plot ty, and you'll have the plot of the solution, okay? Now, how many elements in t and elements of y? You don't know until you call it. MATLAB will decide based upon certain algorithms of basically to get a good sample for plotting how many points does it have to output. That's beyond, you can't, there are ways probably overriding that, okay? But the best thing is to let MATLAB do its job, and it'll come out with enough elements in t and y that you should get a smooth picture. If you don't get a smooth plot, you can always modify it, okay? But it's very intelligent in that way to make sure that, you know, because I go from, you know, t equals, what am I starting at, -2 to 15. How many points in between? 3 points? 1,000 points? Okay? You have to have enough that you can really see a nice smooth curve going through there. And MATLAB will decide that actually automatically. Okay, so let's go now and see where's that routine that calculates the x dt given t and x. Okay? And then we'll use the solver. Okay? Okay, need that for reference because I don't remember all these things. Okay, what do I call this one? Probably OGE1.m, that's what I called it. Okay, look how, look at it, it's a very small routine. Here it is. Okay, it's a function, so the first word is always function, and all these, when you go over, it's always going to be function, okay? The left is the output, okay? And then you need the name and 2 arguments. Notice what I called the output, I made it suggestive. Okay, in the documentation it says y, but I'm doing x, so I just call it x dot. Okay? Okay? So this routine basically, given a t and x, has to calculate x dot. Okay. Now, what I should tell you is that many times you'll have differential equations where perhaps dx dt is only a function of t, or it may just be a function of x. However, the way MATLAB is set up, you must supply both of these, even if they don't appear in the derivative. In our case, they do, okay? But I could, for example, have, say, x dot equals t squared sine t, right? Okay, and therefore x is never used, but you always have to have them like that, okay? It always expects the name of the function and two arguments, the independent variable and the dependent variable. Because that handles the most general case, where the derivative is indeed a function of the independent and dependent variable, okay? Which is what we have. Okay, and again, it's the same thing, it has to be vectorized. So don't think you just have a t equals 1 and x equals 6, okay? You're coming there, the solver has, in its own way, decided, I need that derivative at the following tx points, okay? So t is going to be a vector coming in, and x is going to be a vector coming in. And you better calculate dx dt, or x dot, as a vector corresponding to that tx pair. T1 with x1, T2 with x2, etc. Okay, so on the left-hand side we have x dot, that's fine. What's the first term in the derivative? We need the elements of x squared. And notice I put the dot there, all right? I don't want to take the vector x and multiply by itself. I want to take every element of x and multiply by itself. So that basically gives me the x dot squared. And if x, for example, for argument's sake, says was a 50 by 1, this is going to be a 50 by 1 vector of x squareds, right, coming in, okay? And then t squared over t to the fourth plus 1, exactly the same, okay? Remember, t is a vector. You don't want to square t. You want to take every element in t and square it. So it's t dot squared, okay? Same thing over here. The denominator t to the fourth plus 1, when you code it up, you have to remember every element of t to the fourth power plus 1. And then when we subtract, obviously they'll be exactly of the same length, okay? And we'll get this vector of dx of x dot, however big x and t are, at all those corresponding points. And that's all this routine has to do. Okay, you come in with the independent variable and the dependent variable, assume they're vectors, and you have to then write the formula to calculate the first derivative, dx dt. Okay? Now, this is an example of just one equation, okay? Later on, I'm gonna show you, I'm gonna do a simple pendulum, which comes out to be two equations. You can have systems of differential equations in MATLAB. It doesn't have to just be a scale, what's called a scalar equation. Let's start off with this one, because it's the easiest, okay? So, we got our function, it's called ODE1, okay? So let's go now to the solver, okay? And again, let's remind ourselves of the syntax, okay? Let's see. Okay, I got the solver, I need the function, the time span, and the initial value, okay? And a vector coming out. Okay, so let's do it this way. Again, let's use our own notation, okay? Okay, so the output is always in brackets, sorry, bracket, okay. Again, t values and x values coming in, and the order is important. So tx is going to be tx is going to be an two arrays that are computed by MATLAB, right? Okay, and it was ODE 45 of. Okay, what's the first argument to ODE 45? It's basically a handle to that function. It's that guy that calculated the dx/dt. We just went over that. You have to do the @ symbol, and it's ODE1, I believe, is what we call it, right? Okay. What's the next argument if you look at the documentation? It has to be that t-span, right? So let's put that in. T-span now, you put over here, remember it's a vector. How do we enter a vector? You just put a bracket. And I believe once it says a row vector, so we'll go from -2, because that's where the initial position is, up to 15 seconds. Okay, so there's your t-span. That's done. Now, of course, what you could have done is you could have written a line above this, t-span equals -215, and put in the word t-span as opposed to putting in brute force like I did. As long as it knows what it's doing, as long as it supplied the right information, it doesn't matter if you put numbers in there or you put a variable containing those numbers. And the very last argument is your initial value of x, which is 0.55. Right? Okay. And that's it. And again, I don't want to see the output over here at this point. So hopefully it'll work. and it'll give me arrays of t and x that have the solution. Okay, let's do a whose. Because remember I told you, you don't know before you solve it what the dimension of t and x is going to be. They better be the same. Let's see what MATLAB decided to do. It decided that I need 53 points, okay, to get a good solution, and obviously x is 53, right? They're both 53 by 1. So to see the solution, plot t comma x. That's all it is, right? Let's see what the plot looks like. Oh, here it is. That's good. No. Okay, I'm sorry, I don't know what happened over here. Oh, here it is. It's hiding over there. Okay, there it is. Okay? Something which would be very hard to predict from the differential equation. Let's at least get some confidence that it put it through the point minus 2.55. If I go to minus 2 over here, you can see, right? 0.55, right? That's where it started at. So it seems that this function, you know, starts to decrease, then it gets a little peak, it decreases, reaches a minimum over here, but who knows what happens after 15 seconds? I have no idea, okay? You'd have to integrate further, okay? So this is using MATLAB to solve a rather complicated nonlinear equation. And as long as you can calculate the XDT, this thing could be, you know, 5 lines long, 100 lines long, it doesn't make a difference. As long as you can calculate the XDT in terms of x and t, the solver will give the solution for you. Okay. Any questions on that? Okay. Now what I want to do is something interesting, okay? And you've probably never seen this before, but I think it's something which you'll find, you know, pretty interesting. It's basically a simple pendulum problem, okay? And we actually wrote this equation down maybe the first or second class, okay? It's basically, we're going to look at a simple pendulum and write down the exact equation of motion, okay? Have MATLAB solve that numerically. You can't do it analytically, obviously. And then we look at the linear equation and have MATLAB solve that. And the question is, when can you basically get by with the linearized solution of the problem? And kind of intuition tells us that if we pull the pendulum to the, you know, to the side and don't make the angle too large, then, you know, it should be pretty good. But the question is how large? 10 degrees, 30 degrees, 60 degrees? So I made up a problem here. I forgot what the numbers are. We'll see. One is a relatively small angle. The other one is relatively large. And you'll see the deviation between the linearized solution and the exact solution. So again, let's just remind ourselves what we have over here. So this is just a vertical. We've got a pendulum, mass m, okay? And it's a massless rod, right? And the equation, the exact equation, is second derivative theta with respect to time plus g over L sine theta is equal to 0, okay? That's the exact equation of motion. That's exact. And we know that's nonlinear. Why is it nonlinear? Because it's the sine of theta, right? It's not a linear operator. Okay. And what's done in elementary physics courses, you can say, they'll say for theta small. And again, I'll put small in quotes because what do you mean theta small? That's what we're going to investigate, okay? So for theta small, sine theta is approximately equal to theta. So we get an approximate equation of theta double dot plus g over L theta is equal to 0. Actually, you can solve this analytically. We're going to be doing that, you know, very soon. You get sines and cosines, okay? But, you know, I'm going to just do everything in MATLAB, okay? Since the point here is to learn MATLAB, okay? And now, of course, to get the unique solution, we need theta at time 0, right? That has to be specified, okay? And remember, this is all in radian measure, okay? So if you do 60 degrees, remember to multiply that by pi over 180, okay? And then, what'll be interesting is that, you know, we'll look at this solution versus this solution. In one case where theta of 0 is relatively small angle, another case where it's relatively large, and you'll see that in one case the graphs pretty much overlay, in the other case they start to deviate right away, okay? So this is basically the answer. I'm doing a simple pendulum, but you know, you can imagine in practice you would get, you know, some type of complicated system that you're modeling, and the real equations are nonlinear, okay? And the control engineers always come to you. They love linear models, control guys, okay? It's always because they're in love with Laplace transforms and transfer functions, and they always say, "Can you give me a linear model?" okay? And in order to do that, give something reliable, you have to say, gee, can I linearize this or not, okay? So this is an example, albeit very elementary, of how you would do that type of operation. Okay. Oh, let me tell you one thing over here, basically, that we have to do. We have to do some work on this, okay? We have to write this as a system, okay? If you look at MATLAB, okay, look at the ODE solvers, okay, it's always a first order system, okay? It can do, right, we did a first order equation, it only does first order equations. You say, gee, that's pretty lousy, you know? All my mechanics is second order. But there's a standard way of converting this second order equation into a system of first order equations. Let me see what variables I used. Okay, let me show you how to do that, okay? So I'm going to say, let y1 equal theta of t. Okay? That seems kind of stupid, right? Because I'm saying basically, calling theta y1, okay? But let me show you what the next step is. Let y2 equal d theta dt. Okay? Now what we're going to do is write two simultaneous differential equations. y1 dot equals and y2 dot equals. And MATLAB can do that. Okay? So, what do I have? What's the derivative of y1 with respect to time? Now you do everything now. Remember, you want to write down for MATLAB y1 dot as a function of t, y1, and y2. Okay. Well, y1 dot is just theta dot. Sorry, yeah, y1 dot is theta dot, which is y2. Seems kind of silly, but the idea now, we're going to be able to write as a system, right? You can't argue with that, right? If y1 is the angle theta, then y1 dot is going to be theta dot, which I just said was y2. And now the differential equation comes into place. What's the derivative of y2 with respect to time? Okay? That's theta double dot, and we can get that from the differential equation. It's minus g over L. Let's use the nonlinear sine of theta, but what's theta? y1. So that would be y2 dot if for the nonlinear equation. Okay, I should put that down. That's for the nonlinear case. And for the linear case, you'd have the derivative of y2 with respect to time is equal to what? Well, that's theta double dot minus g over L theta. Minus g over L, but what's theta? That's just y1. Okay? So, I'm going to write two routines, one for the linear pendulum, one for the nonlinear,